In this hour, we will be talking about types of frequency responses that can be realized by a first order circuit. We begin by a low pass filter. Okay. Now consider the following example where this circuit, which is first order, has the following topology. So this is our input, that is the voltage provided by the independent voltage source, and this is where we collect the output. Okay, the out. That is the it's the voltage drop across the terminals of the resistor. Okay, R, and this is the inductor with impedance SL. Okay. Now, to determine what type of frequency response this circuit should produce, what we would do formally is we obtain the transfer function, okay, from this input to that output, the out, and then by plotting the gain of H omega, where H of S is the transfer function, we can see the type of, we can determine the type of the frequency response that this first order circuit would produce. Okay, but since the circuit is quite simple, we can do that even before obtaining the transfer function. Okay, so here we have, I mean, this is how it can be done, or it can be seen. Here we have an inductor. Okay, we know that at DC steady state, inductor behaves like a short circuit. Okay, so when this is short circuit, all the voltage, the input voltage, will appear at the terminals of the output resistor. Okay, out, and then the impedance of the inductor is J omega L. So that means as you increase the frequency omega from very small frequencies close to the DC steady state, okay, where we can take omega equals 0, to larger and larger frequencies, the impedance, the magnitude of the impedance J omega L becomes larger and larger. So at very high frequencies, this inductor will behave like an open circuit. So this being open circuit would mean there'll be very little current flowing over R, and very little current would mean very little voltage that's being produced at the output. So at low frequencies, therefore frequencies close to DC, this is almost short circuit more or less. So we see a significant portion of the input voltage at the output. At very high frequencies, this almost behaves like an open circuit, and we see a very little amount of voltage, a very little amount of input at the output voltage. Okay, so that means this circuit should produce a low pass. Okay, this should produce a low pass characteristics. So let's also verify this qualitative analysis by obtaining the transfer function. So H of S equals, by voltage division, okay, H of S is transfer function V0 over Vin equals R over the impedance, overall impedance seen by the input voltage, which is R over R plus SL. Okay, therefore H omega equals, can be written as R over L divided by R over L plus J omega. Okay, when you look at this H omega, it's clear that at very low frequencies, when omega is close to 0, so what we have is, we can just ignore this, and what we have is RL over RL. The gain is close to unity. As omega increases, the magnitude of the denominator term increases. The magnitude of the numerator term is always R over L. It's fixed. Therefore, as you increase omega, the gain or the magnitude of H omega becomes smaller and smaller. So that means at high frequencies, not much will be observed, okay, at the output, whereas at low frequencies, when omega is small, we will see something significant at the output terminals. Therefore, this circuit produces a low pass type of filter. Okay, now the general form of a first order low pass filter is this: H J omega equals K over alpha plus J omega. Okay, in our case, alpha and K, they are the same, but in general it has the following form. Okay, where alpha is positive, because we have to be working with a stable circuit in order to be able to talk about sinusoidal steady state. Otherwise, nothing makes sense. Okay, so for this H omega, let's obtain the two functions that are essential for the frequency response, namely the gain function, the magnitude of H omega, and the phase function, that is the phase of H omega. Now the gain function H J omega reads following. So K could be positive or negative. Okay, so when you talk about the gain, you take its absolute value, and then as for the magnitude of the denominator, what we have is alpha squared plus omega squared. Okay, so let's write this in the following form, which will make us see certain things in a clearer light. 1 plus omega over alpha square, and then we take the square root of the whole. So that's the gain function. How about the phase function? Okay, theta of omega equals, now the phase of H omega simply is the phase of the numerator minus the phase of the denominator. Now if K is positive, so K is, first of all, it's real, okay? If it's positive, then its phase is 0, therefore it will have no contribution to theta. And what we have is, for K positive, phase of H omega equals 0 minus the phase of the denominator term. And the phase of the denominator term is arctangent omega over alpha, okay? So therefore, for K positive, we have minus arc tangent omega over alpha for K positive. For K negative, what you do is, to this you add a phase of 180 degrees, okay? Because a negative real number comes with a phase of 180 degrees, or pi radians. Okay, 180 degrees minus arc tangent omega over alpha for K negative. Okay, now let's obtain the plots so that we see what we expect to see, or we see the low pass behavior. Okay, let's obtain the gain plot first. Okay, so this is our gain, Hj omega magnitude. This is 0 and this is omega. Now, this is our gain, Hj omega, okay? So, so the denominator, first of all, the numerator is fixed at magnitude of K divided by alpha, and the denominator is such that the lowest value that it takes clearly is when omega equals 0, and as you increase omega further and further, the denominator becomes larger and larger, and the overall magnitude therefore becomes smaller and smaller. So that means the highest that this term can achieve is for the case when omega equals 0, because that makes the denominator as small as possible. When omega equals 0, this thing is 1, denominator is 1, and the gain is magnitude of k divided by alpha. And then as you increase omega, denominator becomes larger and larger, and as omega goes to infinity, the denominator tends to infinity, then the whole thing tends to 0. So what we have for the gain function is we have a monotonic behavior starting at its maximum value, which is magnitude of k over alpha, and then decaying to 0 as omega goes to infinity. Okay. And then as for the phase, omega, this is theta omega. Suppose that this is 0 degrees. Okay. For the case k positive, this is the phase of the our low pass filter, which is minus arctangent omega over alpha. Let's forget about this minus. Okay. So omega, for omega equals 0, what we have is 0 degrees. As omega increases toward infinity, what happens is, since we're talking about arctangent and alpha is positive, we're heading toward pi over 2 radians or 90 degrees. But we have a minus sign in front, so that means we start from 0, and as omega goes to infinity, we approach to minus 90 degrees. That's the case for k positive. Okay, so this is where we're heading to minus 90 degrees. And we have this monotonic shape. Okay, now what we have figured out is max omega h j omega equals, so the maximum value that the gain function attains is, we don't have to do any formal analysis. It's clear when you look at this fraction, it's clear that the maximum that it can achieve is the value of the numerator, which is k over alpha. Okay, magnitude of k over alpha. Now, since we know the maximum value, we can figure out, by using the definition of cutoff frequency, we can figure out the cutoff frequency. Note that the cutoff frequency, which is the frequency that determines the border between passband and stopband, that frequency is such that, so let's remember this definition, the gain at the cutoff frequency, or cutoff frequencies, if you have more than one cutoff frequency, is such that it equals 1 over square root of 2 times the maximum gain of the gain function. Okay, so what we have is 1 over square root of 2 times max h j omega magnitude. So that was our definition. Okay, now this is the maximum value, and then this divided by square root of 2 must be the value of the gain function at the cutoff frequency omega c. And then by applying this definition, it's clear that the cutoff frequency should be such that this omega over alpha equals 1. So we have 1 and 1, that makes square root of 2. So when omega equals alpha, we have this term 1 over square root of 2. Therefore, the cutoff frequency must be equal to alpha. Okay, so omega c must equal alpha, the cutoff frequency. Okay, so this is k over square root of 2 alpha, and the frequency corresponding to that is what we're calling as the cutoff frequency. And we just figured out that the cutoff frequency for our low pass filter, whose general form is here in the box, equals alpha. Okay. Now what happens at the cutoff frequency to the phase? Let's also check that. This is our phase, okay, for K positive. When you plug in omega equals cutoff frequency, which is alpha, what you have is alpha over alpha 1. Arctangent 1 is 45 degrees, and we have a minus sign in front. Therefore, at cutoff frequency, omega C equals alpha, the phase is minus 45 degrees. Okay. Now, so for our filter, let's figure out the simple details associated to it. What we have is, or what we have to determine is its passband, its stop band, and the bandwidth. Okay. So the cutoff frequency marks the border frequency between passband and stop band. Therefore, this part is the stop band. That is, the frequency is larger than cutoff frequency, or larger than alpha. And this here, from 0 to alpha, is our passband. Okay. So omega alpha is our passband, and all the other frequencies, namely omega larger than alpha, those frequencies make our stop band. And bandwidth, by definition, is the length of the passband interval. In this case, the length is alpha. Okay. B equals omega C, and that equals alpha. Okay, now let's talk about the other possibility that can be achieved by a simple first order circuit, namely the high pass characteristics. Okay, as before, let's start with a simple example. Plus minus V out. Here we have V in. This is R. Okay. In the previous example, which was an example for low pass, here we had an inductor. Now we replaced the inductor with a capacitor whose impedance is 1 over CS. Okay. Now, before obtaining the transfer function, let's try to figure out the type of gain characteristics that circuit will produce. Again, all we have to do is, because this is a very simple circuit, all we have to do is what happens at very low frequencies and what happens at very high frequencies. Now, the low frequencies can be approximated or can be studied through the DC steady state. Okay. At DC steady state, what we know is that the capacitor behaves like an open circuit. Okay. So that means at low frequencies, capacitor behaves almost like an open circuit. So at low frequencies, therefore, there will be very little current flowing over the resistor R. Little current means little voltage, so that means at low frequencies, not much of the input signal will be observed at the output. Okay, so at low frequencies we don't see much of the output, much of the input at the output. Okay, what happens at the high frequencies? The impedance of the capacitor is 1 over j omega C. As you increase omega further and further, what happens is the impedance, the magnitude of the impedance becomes smaller and smaller. So that means at high frequencies, at very high frequencies, capacitor can be approximated as a short circuit. So if it's short circuit, or almost like a short circuit, that means most of the voltage, the input voltage, will appear across the terminals of the resistor. Okay, so that means At high frequencies, we'll see much of the input appearing at the output terminals. So, to summarize, at low frequencies, we don't see much at the output. At very high frequencies, we see most of the input appearing at the output terminals. Therefore, this simple circuit should produce high pass characteristics. Okay, so let's verify this by also obtaining the transfer function. H of S, the transfer function, which is V out of S divided by V in of S, equals, by simple voltage division, R over the impedance seen by the input source, okay, which is R over R plus 1 over SC, okay, and that can be written as S over S plus 1 over RC, okay. And in general, so this transfer function, as we have just argued, will produce high pass characteristics. And in general, a first order high pass characteristics has the following form: H G omega equals, okay, K G omega over alpha plus G omega. In this special example, the K is 1, but in general it can be different than 1. Okay. And as before, we have to consider the alpha greater than 0 case, because we have to be dealing with a stable circuit. Okay. Now for this H omega, let's obtain the gain and the phased functions. Okay, now the gain function H J omega magnitude equals the magnitude of K, because K could be either positive or negative, omega over alpha square plus omega square, and then you take the square root. Okay, the magnitude of the numerator divided by the magnitude of the denominator. And let's rewrite this in the following form, which will make certain things easier to see: plus alpha over omega square, and then you take the square root. Okay, and then how about the phase? As for the phase, we have the following. Phase function. Theta omega equals. Okay. This is H omega. Therefore, the phase of H omega is the phase of the numerator minus phase of the denominator. Phase of the denominator is arctangent omega over alpha. Okay. And phase of the numerator is phase of K. Okay, if it's K is positive, then its phase contribution is 0, because the phase of it will be 0. And then plus phase of G omega, and phase of G omega is always 90 degrees, okay, independent of omega. So therefore, what we have is, for K positive, we can simply ignore it for phase considerations. The phase of G omega is 90 degrees, and phase of the numerator is arctangent omega over alpha. Therefore, for K positive, the phase is 90 degrees minus arctangent omega over alpha. 90 degrees minus arctangent omega over alpha. Okay, this is for K positive. And as if K is negative, then what you do is you add to this phase 180 degrees. So that produces 270 degrees minus arc tangent omega over alpha 4k negative. Okay, so the gain function is here, and we have the phase function. Now let's obtain the frequency response plots. Okay, omega, and here we have the gain. Okay, this is our gain function. The numerator is fixed, it's the magnitude of k. And here we have the denominator in terms of omega. So what happens at omega equals 0? We have alpha over 0, so that's infinity. The whole denominator becomes infinity, therefore something divided by infinity that produces 0. So at omega equals 0, what we have is we have 0 gain. So what happens as omega increases? As omega increases, this term decreases, therefore the whole denominator decreases, and as a result the gain function is increasing. Okay, and what happens? What happens as omega becomes larger and larger? As omega becomes larger and larger, this term becomes smaller and smaller, and for very large omega we can ignore it, and what remains is 1. So at very high frequencies we have the gain equals the magnitude of k. So what happens therefore is we start from 0 gain, and as omega increases we're approaching monotonically to the denominator, which is k. Okay, so here is the gain function. Okay, and the maximum is attained at infinity, and that's magnitude of k. So that makes the cutoff frequency equals what? So this is the maximum gain that we can achieve. Divide that by square root of 2 and look at the frequency at which this value is attained, k over square root of 2. Now it's clear that if omega equals alpha, this is 1, 1, 2, then k over square root of 2 is achieved. So that means the cutoff frequency for our high pass filter is omega equals alpha. Okay, so omega c therefore equals alpha, the cutoff frequency. And once you have the cutoff frequency, you immediately have the pass band, stop band, and also the bandwidth. This is the stop band. Okay, the frequencies from 0 to alpha. Frequencies larger than alpha, those frequencies make our pass band, and the length of pass band, which in this case is infinity, make the bandwidth of our high pass filter. Okay, so let's put that down. Max omega h g omega equals the magnitude of k. Okay, so that's maximum that can be achieved, and then k over 1 plus alpha over omega c squared, and then you take the square root equals the maximum divided by square root of 2. So using the definition of the cutoff frequency, we see that cutoff frequency is alpha. Okay, and how about the gain? Excuse me, how about the phase? So let's consider k positive situation. So what we do is at omega equals 0, arctangent 0, that produces 0. So the overall phase is 90 minus 0, which is 90. So we start from phase 90 degrees, theta omega, omega. Okay, and suppose that this is 0 degrees. And what happens is, as you increase omega further and further, this arctangent term becomes closer and closer to 90 degrees. Therefore, in the end, what happens is 90 minus 90, we're going toward 0. So this is the shape of the phase plot. And let's also see what happens at the cutoff frequency. At the cutoff frequency, omega equals alpha. If you plug in omega equals alpha here, what we have is alpha over alpha which is 1, arctangent 1 is 45 degrees. 90 minus 45, that produces 45. Therefore, at cutoff frequency, omega c equals alpha. The corresponding phase for K positive is 45 degrees. Okay. So once again, what we have obtained is, we obtained that the passband is the frequency, the range of frequencies for which omega is larger than alpha. Omega larger than alpha. Stop band is what remains when you take those frequencies outside. So 0 omega less than alpha. And the bandwidth by definition is the length of the passband window. In this case, that length is infinity. Okay, for our high pass filter. Okay, so this is for K positive. Okay, now let's talk about an example. So this is our circuit where we use an operational amplifier. This is where we apply the input voltage, and this is where we collect the output voltage we out. Okay. The resistances of 3 resistors are identical and given as R, and here we have a capacitor with capacitance C. Okay. Now for this circuit, we are asked to perform the following. Find the transfer function of this filter. H of S, which is V out S over V in of S. And by looking at the transfer function, determine the type of the filter. Okay. Low pass or high pass, and figure out the passband gain. Okay, and for resistance values taken to be 10 kilo ohms, design the circuit or choose the capacitance value C such that the cutoff frequency equals 500 Hertz. Okay, and finally obtain the phase shift at that frequency, at cutoff frequency. Okay, so let's proceed with the solution. Okay, suppose that we transform the circuit to S domain. So the resistances are still resistances R, and here we have the impedance of the capacitor, which is 1 over SC. So this node is node voltages V minus, and this node voltage is V plus. So what we have is V plus equals, okay, we're dealing with an ideal op-amp, say, so there will be no current escaping into the op-amp, and this part will simply behave as a voltage divider. Okay, the voltage appearing across terms of R, which is V plus, simply equals R over the impedance seen by the input, okay, which is R plus 1 over SC times the input voltage. So what we have therefore is V plus equals R over R plus 1 over SC times the input voltage. Okay, and that can be written as RCS over RCS plus 1 times the input voltage. As for V minus, this too is a voltage divider, and since the resistances are equal, so what we have is V minus simply equals V0 over 2, again due to the fact that there is no current escaping to the op-amp through the negative terminal. Okay, and then the op-amp is in linear region because we're talking about a transfer function. In order to be able to talk about transfer function, the circuit should be LTI, and this circuit is LTI when the op-amp is in linear region. Under that assumption, we have V plus equals V minus, and equating this expression with that immediately gives us the transfer function H of S. So V plus equals V minus implies RCS over RCS plus 1 V in equals V minus VR over 2, and that produces the following transfer function. H of S equals 2S over S plus 1 over RC. Okay, so what we have is we have a high pass filter. Okay, so BH J omega is 2J omega over 1 over RC plus J omega. In other words, the filter is a first order high pass filter. Okay. Now passband gain well, there's not a fixed gain throughout the passband, okay? Because the gain function is not like step-like function, but we can approximate it as a step-like function. And if you do that approximation, what you do as the passband gain usually is the maximum gain that can be achieved by your transfer function or by your filter. So max omega H G omega equals 2, okay? That follows from our previous analysis, this number here. Okay, now, so that's C. For D, we have to figure out the capacitance value so that the cutoff frequency is 500 Hertz. Now, the cutoff frequency was equal to alpha, that follows from our previous analysis, and alpha in this case is 1 over RC. Okay, so by equating omega C equals 1 over RC, R is given, omega C is given, we will be able to figure out the capacitance value C. So let's do that. Okay. Now the cutoff frequency once again equals alpha, and alpha is 1 over RC in this case. Omega C equals 1 over RC. So we're not given omega c, but we're given f of c. Okay, one is in hertz, the other is in radians per second. So what we do is from that f of c or fc we obtain omega c, and omega c is 2 pi times fc, the frequency. That's how we transform hertz to radians per second. So 2 pi fc equals 1 over rc. Okay, so that means 2 pi fc is given to be 500 hertz, and that equals 1 over the resistance values are given to be 10,000 ohms. Okay, so what we have is 10 to the 4 times C, and from this we obtain the capacitance value. So that produces C equals 1 over 10 to the 7 times pi farads, and that's approximately 32 nanofarads. Okay, so that's the capacitance value that produces 500 hertz of cutoff frequency. And finally, let's figure out the phase shift at the cutoff frequency. So what we're dealing with is we have to figure out the phase of the transfer function, okay, hg omega, evaluated at omega equals omega c, or omega equals alpha, alpha being 1 over rc. So that equals, okay, 2j, omega equals 1 over rc, 1 over rc plus j 1 over rc. Okay, so we're plugging in omega equals alpha, or omega equals 1 over rc, and that produces, you can cancel, simplify 1 over rc's, and what remains is the phase of j2 over 1 plus j. Okay, and that equals the phase of j2 minus phase of 1 plus j. The phase of j2 is, this is purely imaginary, therefore the phase of the numerator is 90 degrees, and phase of the denominator is, we know that the phase of 1 plus j is 45 degrees. Okay, therefore 90 degrees minus 45 degrees, that produces 45 degrees. Okay, so that's the phase shift at the cutoff frequency. So which means that if you drive the circuit with an input at the cutoff frequency, okay, the phase of the output will be the phase of the input plus 45 degrees.